Welcome viewers, in this video we'll see the comparison between single and three-phase AC system. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The comparison between single phase and three-phase AC system. We'll see the definition. This is the description, the single phase, and third column is the three-phase. First we'll see the definition. For single phase, the power supply through only one conductor. The supply is going by only one conductor. In case of three phase, the power supply through three conductors. There are three conductors are available. We'll see the waveform. This is the waveform of the single phase AC supply, voltage waveform. The x-axis time, y-axis voltage. So AC means we know that alternating current. Initially the value is 0, then voltages keep on increases and reaches the maximum value at 90 degree. Thereafter decreases and reaches the zero value at 180 degree. This is called a half cycle, right? Then again it increases in negative direction and reaches the maximum value at 270 degree. Again start decreases and reaches the zero value at 360 degree. This is another half cycle. So the total cycle is called a full cycle. This is called positive half cycle and this is negative half cycle. 0 to 90 increases, 90 to 180 decreases, 180 to 270 again increases in negative direction, 270 to 360 again decreases in negative direction. This is positive half cycle and this is negative half cycle. Entirely it is called a full cycle, having only one voltage waveform. While going to the three phase AC supply, where three voltages are available: R, Y, B. Voltage across R phase, voltage across Y phase, voltage across B phase. That sequence is RYB, red, yellow, blue, right? So the red voltage red phase starts at 0 degree. It goes like a single phase, it will keep on going. The Y phase starts at 120 degree. There is a 120 degree phase displacement between each and every phases. So R phase, red phase starts at 0 degree, Y phase starts at 120 degree. Then it will keep on going as a alternating current. Then this B phase starts at 240 degree, right? Then then keep on, it's going. So R phase 0 degree, Y phase 120 degree, B phase 240 degree, right? It's keep on going. In case of single phase, if we add positive half cycle and negative half cycle, the net voltage will be 0. For example, here 100 voltage means here minus 100 voltage. By adding both full cycle, the net value is 0. But that not happen in the three phase system. See this, at 0 degree R phase increases in positive direction. This B phase is decreasing in negative direction. At the same time, this Y phase is increasing in a negative direction. So one phase increasing, another phase decreasing, means the net value will be there. The sum of these three is the resultant value. Here the resultant value will be 0, but here resultant value is not 0 because R phase starts 0, Y phase start 120, B phase start 240. At the given time, one phase is increasing mean another phase decreasing mean the resultant value will be always available. It is around 1.67 phase voltage, right? So the three phases available, the three phases will not got cancelled. The resultant value almost available 1.637 times of the resultant voltage. That is the main advantage of the three phase system. In single phase, entire positive half cycle, if you add, it becomes 0. But here always some voltage will be available because of three phases displaced with 120 degree. That is around 1.67 times of output voltage, right? Now we'll go to the remaining definitions. The third one is the number of wires. Require 2 wires for completing the circuit. The single phase AC system we already discussed, only one conductor. For returning we need one more conductor, that is totally we need 2 wires. Phase and neutral. One is for phase, another one is for neutral. Here require 4 wires for completing the cycle. 3 for 3 phases, R, Y, B. One is the neutral, right? The fourth wire is the neutral. Here phase and neutral, 2 wires required. Here R phase, Y phase, B phase 3 wires required, and N phase, that is N, neutral, one more wire is required. So totally we require 4 wires, right? So phase neutral 2 wires, R, Y, B neutral 4 wires. The voltage is around 230 voltage. The voltage is 230 voltage in a single phase. In the 3 phase we are measuring phase to phase. So around 415 voltage. Here we are referring phase to neutral. So phase to neutral around 230 voltage will be there. But here we are referring phase to phase. So one phase around 220 voltage will be there. Another phase another 220 voltage will be there. So while measuring phase to phase is around 415 voltage. This is standard value 415 voltage. Then phase name, split phase. Only 2 phases away. Only 2 wires. So this split phase. No other name. R phase, Y phase, B phase. Right. The network is, it is simple because we have only 2 wires, phase and neutral. But this is complicated. 3 wires are available. We can need to go with the phase displacement, current, voltage, everything. We need to concentrate. Then the losses. Losses are maximum. Here losses are minimum. Why losses are maximum? We have already discussed. Only one phase is available. The sum of 2 got 0. Positive half cycle plus negative half cycle if we add, that will be 0. Right? But here 3 phases available. At a given time we are got 1.6 time. So always the voltage is utilized by the load. Here all the load may be got losses. There may be losses due to only one phase. Right? Now we'll go to the remaining parameters. The next one is the efficiency. Efficiency here less, here high, because 3 phase we are utilizing maximum voltage from the 3 phases. Here the efficiency will be lesser. Economical also very lesser. For erecting the single phase we need pole, everything, but we have only one phase is available. For the same pole we can transmit 3 phases. At a given time 3 phases are available, so the economical will be more. For usage, for home appliances, the load available in the home we are using single phase. Fan, tube light, the refrigerator, AC, for that we are using the single phase supply. In 3 phase supply, large industries and for running heavy loads. For single phase we are getting only 230 voltage. While going with the 3 phase we are getting 415 voltage. So in that automatically the current also increases. So the total power will be increases while using 3 phase power, voltage as well as current. So we can go with a industrial application, that is for heavy, running the heavy loads. Heavy loads definitely we need 3 phase. So the voltage level increases, so that automatically the current level will also increases, so that we are able to run the heavy loads using the 3 phase AC system. So in this video we discuss about the comparison of single phase and 3 phase. So the single phase we are having only 2 conductor, phase and neutral, used for the home appliances. And 3 phase we have 4 wires, R, Y, B and neutral. That is normally used for industrial application to run the heavy loads. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the generation of a 3-phase EMF. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, how the 3-phase EMF is generated. Let us consider this diagram. There is a magnet available. So both the side we have magnet, N pole and S pole. There are 3 conductors available. Because of 3 phase we are having 3 conductors are available, named as R, Y, B. Red phase, Y phase and B phase. Then each and every phase is displaced by 120 degree. There is a red phase and Y phase. Between red and Y phase there is a 120 degree phase displacement. Then B phase and Y phase, there is a displacement of 120 degree. From B phase to R phase there is a displacement of 120 degree. So each and every coil, these 3 coils, red, yellow, blue, are displaced by the 120 degree, placed at a distance of 120 degree, right? R and Y 120 degree phase displacement, Y and B 120 degree displacement, B and R 120 degree displacement. Right. Now we'll see what is the working principle. According to the Faraday's law of electromagnetic induction, we know that whenever a coil rotates in a magnetic field, there is a sinusoidal induced EMF in that coil, right? Based on the Faraday's law, whenever the coil rotates, this coil is rotating in a magnetic field. It is placed in a magnetic field. Whenever a coil rotates in a magnetic field and sinusoidal induced EMF is in that coil. EMF is induced in the coil. The nature of induced EMF is the coils are already displaced at 120 degree, so the induced EMF also 120 degree displacement. That is the 120 degree displacement between red, yellow and blue, right? So coils are displaced by 120 degree, so that the induced EMF also displaced by 120 degree. So we will see the further details of this, how the EMF is generated. Now consider three coils. C1 refers R phase, C2 refers Y phase and C3 refers B phase, which are displaced 120 degree from each other on the same axis as shown in the diagram, right? Now we consider coil C1, C2, C3 with respect to R phase, Y phase and B phase displaced at 120 degree with the same axis as shown in the diagram. The coils are rotating in a uniform magnetic field produced by N pole and S pole in the counterclockwise direction with constant angular velocity, right? These coils are placed in a uniform magnetic field that is rotating in that uniform magnetic field in a counterclockwise direction with a constant angular velocity. Now we'll see what will happen while rotating. While rotating this, what will happen? We'll see that. According to Faraday's law of electromagnetic induction, EMF is induced in three coils. The EMF induced in these three coils will have phase difference of 120 degree because already the coils are placed at 120 degree. So the EMF induced in that also with a phase difference of 120 degree. That is, if the induced EMF of coil C1 has a phase displacement of 0 degree. Let us consider the first coil C1 R phase. The EMF induced is 0 degree means then the EMF induced in the coil 2 Y phase is lag that C1 by 120 degree. So after 120 degree EMF will be induced in the second coil C2 Y phase and C3 lags by another 120 degree with the C2, right? So the EMF induced in the C3, that is coil B phase, is another 120 degree with the C2. While comparing with C1, it is 240 degree, right? So C1 R phase EMF induced at 0 degree, C2 Y phase EMF induced at 120 degree, C3 B phase EMF induced at 120 degree while comparing to C2, right? So there is a phase displacement of 120 degree between all the three phases. Now we'll see the waveform. This x-axis, the time period is there and also it is given in terms of the degree 0 to 360 degree. Then y-axis is voltage. We have three phases, R phase, Y phase and B phase, right? As we know that R phase starts at 0 degree, right? It reaches maximum at 90 degree and thereafter decreases and reaches 0 again at 120 degree. This is called positive half cycle, right? Start from 0 degree, keep on increasing, reaches maximum at 90 degree, then start decreasing, reaches 0 at 120 degree. Then start increasing in negative direction and reaches maximum at 270 degree. Then start decreasing in negative direction and reaches 0 degree at 0 at 360 degree. This is called negative half cycle. So entirely it is called a full cycle, right? Cycle of a voltage, right? Positive half cycle and negative half cycle. Start from 0, 90 degree, 180 degree, 270 degree, 360 degree. This is called a full cycle, right? It starts at 0 degree. Then the Y phase. Y phase starts at 120 degree. The same process repeat. Increases and decreases. Keep on going. But it starts, there is a phase displacement between R phase and Y phase is 120 degree. Lagging. Y phase is lagging the R phase by 120 degree. R starts at 0 degree but Y starts at only at 120 degree. Thereafter it follow the same procedure. Then this B phase starts at 240 degree. There is a phase displacement of B phase and Y phase is 120 degree. B phase and R phase is 240 degree, right? It starts at 240 degree, the same process repeats, right? See this is the three phase waveform. R starts at 0 degree, Y starts at 120 degree, B phase starts at 240 degree. Just keep on going. So at a given time, there is a some voltage is always available. It is around 1.67 voltage. There are three phases available, but one phase is increasing, another phase is decreasing, and another phase is decreasing in positive. This is increasing in positive. This is decreasing in negative. So by adding these three, almost 1.67 times of voltage is always available. But in case of single phase, while adding positive half cycle and negative half cycle, the net voltage will be 0, right? But here not about 0. One phase, three phases available, alternatively going with 120 degree phase displacement. So automatically we are always get 1.67 times of resultant voltage, right? See this, there is a 120 degree displacement between R and Y phase. There is a 240 degree displacement between R and B phase, or 120 degree between Y and B phase. So based on that, we can see the voltage waveform, the voltage equation. So we'll refer the R phase is the reference phase. Reference will take R, ER, voltage across the R phase. EM sin omega t. EM is nothing but maximum voltage. So it starts at 0 degree, so there is no angle is available. There is no angle available. EY, Y phase, EM sin omega t minus 120, because it starts after 120 degree. So we need to subtract minus 120 degree. Then B phase, EB, equal to EM sin omega t minus 240 degree, because there is a the phase difference between B phase and R phase is 240 degree. B phase starts at 240 degree only, so that we need to subtract 240, right? So R phase EM sin omega t, the angle is 0. Y phase EM sin omega t minus 120, starts after 120 degree. EB equal to EM sin omega t minus 240 degree. B phase starts after 240 degree only. The above equation can be represented by the phasor diagram. We can represent by the phasor diagram that is shown below. So this is the R phase, Y phase and B phase, right? Between R and Y phase, there is a phase displacement of 120 degree. Between R and B phase, there is a phase displacement of another 120 degree. Between B and R phase, another 120. So each and every phase displaced by 120 degree. If we take R phase is 0 degree, mean between R and Y 120 degree. Between R and B 120 plus 120 240 degree, right? So finally it is the displaced, every phase is displaced by 120 degree. So in this video we discuss about the how the three phase EMF is generated. The coils are placed at a displacement of 120 degree between each and every coil. So according to Faraday's law, EMF is induced. That EMF also displaced by 120 degree. We verified with the waveform, followed by the equation, followed by the phasor diagram. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the important definition of a three-phase AC system. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, three-phase AC system, important definition. In three-phase AC system, there are two types available, star connection and delta connection. So for that in this two method, the voltage and current, line voltage and phase voltage will be different. First we will see the diagram of the star connection and delta connection. Then we'll go to the definition. So in the star connection, the similar ends, either start or finish of three windings are connected to a common point. See this is the three phases available. So one end is connected to common point. This is called R phase, Y phase and B phase. In all the three phases, one end is connected. that is called a star or neutral point. The remaining end is connected to the line, right? So this R, Y, B phase, one end is available. Remaining ends are connected together and form the star point or neutral point, right? So the star connection means one end is connected to the common point, star or neutral point. Another ends are available, right? So this is R phase, Y phase and B phase. The voltage between R and Y phase is VRY. This is called a line voltage. The voltage between Y and B is VYB. That is the also a line voltage between Y phase and B phase. Similarly, the voltage between B phase and R phase is VBR, right? So these three are the line voltage. This is the line. This is phase, right? So these are the line voltage. The current flowing through R phase is IR line. This is also line current. The current flowing through Y phase is IY line. Similarly, B phase IB line, right? So these three voltages are line voltages. These three currents are line current, right? While going to the phase, this line current is flowing through the phase. At the time it become IR phase, right? IR, the current flowing through the R phase is called a IR phase. In this star connection, see this IR line is equal to IR phase. Both are equal. The current flowing through the line, IR line, is equal to current flowing through the phase, IR phase. So in the star connection, the line current and phase current are equal. Similarly here, IY phase, current in the Y phase. Similarly, IB phase. Correspondingly, so the currents are equal. The current, line current is equal to phase current. In all the cases, line current is equal to the phase current, right? Now we'll see the voltage. What about the voltage? See, VRY, this R phase is connected here, B phase is connected here. So it is connected to two phases, R phase and Y phase. So VRY is the vector sum of VR phase and VY phase. The line voltage and phase voltages are not equal. This line voltage is the vector sum of two phase voltages. VRY is the vector sum of VR phase, vector sum of VY phase. Similarly, this VYB is the vector sum of VY phase and VB phase, right? So line current and phase currents are equal. Line current is equal to vector sum of phase currents. That is the nature of the star connection. Now we'll go to the delta connection. So in the star connection, in this delta connection, this is the delta connection. So far what we discussed, star connection. Starting end of one coil is connected to the finishing end of the other coil, and so on, which give the closed circuit, right? So the starting end of one coil is connected to the finishing end of another coil. The coils are connected end to end, so that it make a closed circuit. In star connection, only one end of all three phases are connected to make a star connection or star point or neutral point. The other ends are available, freely available to make a line. But here all the end to ends are connected, make a closed circuit. From that the tappings are taken, R, Y and B. The tappings are taken from the each phases, right? So in delta connection, the coils are end to end connected and make a closed circuit. Then the tappings are taken. So this is R phase, Y phase and B phase. The voltage between R and Y phase is VRY. This is called a line voltage. The voltage between Y and B phase is VYB, also a line voltage. The voltage between R phase and B phase is VBR, is a line voltage. The current flowing from the R phase is IR line. Y phase is IY line. B phase is IB line, right? Then now the current is splitted here. IR line is splitted to IR phase and IB phase. So the current is splitted here. So the IR line is the vector sum of IR and IB phase. This is called a phase. These terminals are line. These are all phases, right? Phase voltage and phase current. See this IR line is splitted here. So the vector sum of these two current is nothing but IR line current. Vector sum of phase current is the line current. At the same time, see this, the line voltage VRY is equal to VR phase. The line voltage and phase voltage are both are equal. So in delta connection, line voltage and phase voltages are equal, but the current is vector sum of, line current is the vector sum of phase voltages, just opposite to that of star connection. In star connection, currents are equal, voltage is vector sum. Here, voltage is equal and current is vector sum, right? So this is VR phase, IR phase. These are all the phase current and phase voltages. Now we'll go to the definition. So the first one is the phase voltage. It is defined as the voltage across either phase winding or load terminals. It is denoted by VPH. Right? We already discussed VRY, VYB. Generally it is defined as VPH. The phase voltages VRN, VYN, VBN are the measured between R and N, red phase and neutral, Y and N, Y phase and neutral, BN, B phase and neutral for star connection. Between RY, YB, we are in delta connection. Only in star connection we have neutral point. So that RN, YN, BN. In delta connection is a closed circuit. So it is referred, it is measured between R and Y, Y and B and B and R. Now we'll go next, we'll see the line current, line voltage. It is defined as the voltage across any two line terminals. It is denoted by VL, the voltage between two lines. The line voltages are VRY, VY by VBR measured between RY, YB and BR for star connection and also the delta connection. The line voltage is same for both delta connection and star connection. It is VRY measured between R phase and Y phase. VYB measured between Y phase and B phase. VBR measured between B phase and red phase. Now we'll go to the phase voltage, phase current. It is defined as the current flowing through the each phase winding or the load. It is denoted by IPH. Phase currents are IR phase, IY phase, IB phase. Current flowing through R phase, Y phase, B phase. Measured in each phase of star as well as delta connection. In both star and delta connection, it is represented as IR phase, IY phase, IB phase. Then generally it is measured, it is represented as I phase. Then line current, we will see the line current. It is defined as the current flowing through each line conductor. Phase refers the winding. Line refers the line, load terminal. It is denoted by IL. Line current IR line, IY line, IB line are measured in each line of star and delta connection. Generally it is represented as IL. It is also represented IL line, means R phase line current, IY line, Y phase line current, IB line, B phase line current. Then we will see the phase sequence of the three-phase network. The order in which the three coils, the three coil EMF or the current attain their peak value is called a phase sequence. It is customary to denoted by three phases by the three colors, red, yellow and blue, right? That is, it is finally it is defined as RYB, red, yellow, R phase, Y phase, B phase, that is red, yellow, blue. That is the phase sequence, RYB. Now we'll go to the remaining definitions. Balanced system. What is meant by balanced system? A system is said to be balanced if the voltages and current in all phases are equal in magnitude and displaced from each other by the equal angle. So the balanced system is both voltage and current should be equal in magnitude. Magnitude means values, as well as the displacement between the voltages. That also should be equal angle, right? Voltage and current having equal magnitude and displaced with the equal angle mean that is a balanced system. Unbalanced system. A system is said to be unbalanced if the voltage and current in all three phases are unequal in magnitude and also displaced from each other by unequal angles, right? Both voltage and current differ by magnitude as well as displacement by unequal angle. That is called a unbalanced system. Then we will see the balanced load. What is meant by balanced load? In this type, the load in all phases are equal in magnitude, right? The load is connected to each and every phase. In that, the magnitude should be equal. It means that the load will have same power factor, equal current in them, right? So the meaning is have same power factor and also current drawn is the same. So automatically what is unbalanced load? In this type, load in all phases have unequal power factor and current, right? If you have equal power factor and current, it's called a balanced load. Unequal current and power factor mean unbalanced load. So in this video we discuss what is star connection and what is delta connection in the three-phase AC system and important definitions. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the balanced delta connection, details about the balanced delta connection, relation between line and phase values of voltage and current. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, balanced delta connection. Delta or mesh connection. So the connection is nothing but starting end of one coil is connected to the finishing end of other phase coil, and so as which give the closed circuit. So the starting of one coil is connected to finishing end of another coil and make it as a closed circuit. That is called a delta connection or mesh connection. Now we'll see the diagram. So this is the three phases available, R, Y, B. This phase, R phase, B phase and Y phase. So the one end of the phase is connected to another end of the next phase. So the connected end to end, so that it is become a closed circuit. So that is called a closed circuit. From that the tappings are taken, R phase, Y phase and B phase. So this is the line. This is called a line voltage or line current. At this end, this is called a phase voltage or phase current. So this R phase, Y phase, B phase. The voltage across R and Y phase is VRY. The voltage across Y and B phase is VYB. This is called a line voltage. The voltage across R and B is VBR, line voltage. The current flowing through the R phase is IR line. Current flowing from Y phase is IY line. B phase is IB line. So these are all the line voltage, these are all line current. Now we'll refer the phase voltage and phase current. Now see this RY line is split into two currents, IR phase and IB phase. So the current is split here. Similarly IY line current is split into two, IR phase and IY phase. Similarly IB line current is split into IY phase, IB phase. The current is split, that is the IR line current is the vector sum of IR phase current and IB phase current. So the line current is the vector sum of the phase current. Similarly see the voltage VRY, voltage across VRY is equal to the voltage across the phase R phase, VR phase. Both are equal. VRY is equal to, see the terminal, VRY is equal to VR phase. So VR line voltage equal to VR phase voltage. So in delta or mesh connection, line voltage is equal to phase voltage, right? Line voltage is equal to phase voltage. Similarly line current is the vector sum of phase current. That is the important thing. Voltage, line voltage is equal to phase voltage. Line current is vector sum of phase currents, right? So based on that we can go for the further relation. What are the voltage and current equations are available. So let line voltage VRY equal to VYB equal to VBR equal to VN. So this is a balanced system. So the voltage across the phases are equal. The voltage across RY phase, voltage across YB phase, voltage across BR phase are equal. That is taken as VL. Generally it is line current, line voltage. Similarly phase voltage VR phase equal to VY phase equal to VB phase. That is equal to V phase. All are equal. So generally we termed as phase, V phase. Then line current IR line equal to IY line equal to IB line. The line current in R phase, line current in Y phase, line current in B phase all are equal. Generally it is named as I line. Similarly phase current IR phase equal to IY phase equal to IB phase. That is equal to I phase, right? So because of balanced system, this line voltage, phase voltage, line current, phase current all are equal. Generally it is termed as VL. Line voltage is VL. Phase voltage is VPH. Line current is I line. Phase current is IPH. Right. Now we'll see the relation between this current and voltage. First we'll see the relation between line and phase voltages. For delta connection, line voltage VL and phase voltage are equal. We already discussed in the diagram. Line voltage and phase voltages are equal. So VRY equal to VR phase. VYB equal to VY phase. VBR equal to VB phase. So therefore, line current VL equal to phase current VPH. Right? In delta connection, line voltage is equal to phase voltage. We already discussed in the diagram. Now we'll see the relation between the current. I already discussed line current is the vector sum of phase currents. We'll see the equation. So the relation between line and phase current for delta connection, IR line equal to IR phase minus IB phase, because in the diagram the directions are opposite, so that it is the vector sum means it is minus. One current is flowing one direction, another current is flowing in opposite direction, so that is the difference between these two is the line current. So IR line is the IR phase minus IB phase. Similarly, IY line equal to IY phase minus IR phase. IB line equal to IB phase minus IY phase. Right? So by clearly we discuss in the diagram, line current is the vector sum of phase currents, in that the currents are flowing in opposite direction, due to that we got negative sign. Subtraction, difference between the current. So that is, current in each line is vector difference of two of the phase currents. Vector difference, vector sum, because of negative it is become vector difference. Right? So the line current is the vector difference of phase current. So based on that we can draw the phasor diagram. Phasor diagram relating the current and phase current and line current. Right. Now we'll see that this is the line current, IR line, IY line, IB line. All are differed by 120 degree. R, Y, B. Right? IR line, IY line, IB line. We need to identify, we need to find these values. Right? Our aim is to find the line current. That is the vector sum of these two phase current. So we start with the phase current, IR phase. It is in a x-axis, IR phase. This IY phase having 120 degree phase difference. With another 120 degree phase difference we have IB line. Right? First we will refer phase current, then we will find the line current. IR phase, IY phase, IB phase. This opposite side we have IR minus IR phase. Here opposite side we have minus IY phase. In this we have on the opposite side we have minus IB phase. Right? This minus IB phase. Right? So that this IR, this IR is minus IR. Then this IY minus IY. IB minus IB. Right? So all these phase currents are available. Now we see the vector sum. I will explain again. This is the IR phase current. Opposite side we have IR minus IR phase current. This is IB phase current. Opposite side we have minus IB phase current. This is IY phase current. Opposite side we have minus IB phase current. Right. What is that IR? IR line is the vector sum of IR minus vector difference of IR and minus IB. Right. So vector sum of these two is nothing but IR line. Similarly, IY line is nothing but IY phase minus IR phase. So vector sum of these two is the IY line. Similarly, IB line is nothing but the vector difference of IB and IY. This minus sign indicates difference. That is IB line. Right? So it is very clear. I will explain again. This is IR phase minus IR phase. Then IB phase minus IB phase. IY phase minus IB phase. Now we will see that vector sum of this difference of this IR and minus IB is IR line. The vector difference of IY phase and IR phase is IY line. The vector difference of IB phase and IY phase is IB line. Right? So from this we can frame the equation by using the parallelogram theorem. By using parallelogram theorem we can find the value. Right? So refer this phase RY line equal to vector, this is the square root of RY IR phase, this IR phase, plus IB phase, plus 2 IR phase IB phase cos theta. This is the formula. A square plus B square plus 2AB cos theta. This is the formula from the parallelogram, considering the parallelogram formed by IR and IB, right? So IR line equal to square root of IR phase square plus IB phase square plus 2 IR phase IB phase into cos theta, right? See this, IR is nothing but vector sum of difference of IR and IB. Based on that, the equation is written. We already discussed all the phase currents are equal, so that IR phase square can be written as I phase square. This IB phase square can be written as IB phase square, but all the phase currents are equal, so that 2 into I phase into cos theta, right? So all the currents are now equated to phase current. We already discussed in the previous case. Now we can go for a simplification. So I phase square plus I phase square plus, here I 2 times available, 2 into I phase square cos 60 is 1 by 2. The cos 60 value is 1 by 2, right? I will go for the further simplification. So that I phase square plus I phase square, this 2 got cancelled, plus I phase square, 3 times available. So 3 into I phase square. While taking square root, it is root 3 into I phase, right? I phase square become I phase, right? So IR line equal to root 3 times of I phase current. Line current equal to root 3 times of phase current. Similarly, IY line equal to IB line, that is equal to root 3 I phase, right? And all the line currents are equal to root 3 times of I phase. So that in delta connection, line current equal to root 3 times of phase current. What about the voltage? Line voltage is equal to phase voltage, but current is line current equal to root 3 times of phase current. Current is root 3 times and voltage is equal. Now we'll see one more parameter, power. So 3 phase power equal to V phase plus I phase into cos phi. Similarly 3 times because of R phase, Y phase and B phase. So that is equal to, these 3 times are available. So 3 V phase I phase cos phi, right? So 3 V phase is line, phase voltage equal to line voltage. Both are equal, we already discussed. But phase current is line current by root 3. That is line current equal to root 3 times of phase current. So that phase current equal to line current divided by root 3 into cos phi. So that this 3 is written as root 3 into root 3 in order to simplify. Into VL IL by root 3. This root 3 got cancelled, cos phi. Right? This 3 is written root 3 into root 3. Root 3 into root 3 is again 3. So that we got 3 is cancelled. So that the final value is root 3 VL IL cos phi. So this is the power in the delta delta connection. The power is root 3 times of line voltage, phase voltage, line voltage, line current into cos phi. Root 3 VL cos phi. So in this video we discuss about the delta connection, balanced delta connection, the relation between phase and line voltage as well as current. We observe that the voltage is equal, line voltage equal to phase voltage, but the line current equal to root 3 times of phase current. Finally, we discuss the power also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we'll see the balanced star connection, details of balanced star connection, relation between line and phase values of voltage and current. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. Link is given in the description box. Now we'll go to the topic, balanced star connection, relation between voltage and current for both line and phase values. First we will see the star connection. If the in the star connection, the similar ends, either start or finish, of the 3 windings are connected to a common point called a star point or neutral point, right? Either start or end of the all 3 phases are connected together to make a common point, that is called a star or neutral point. Now refer the diagram. So this is the three phases available, R, Y, B. This is called line. This is three phases available, R phase, Y phase and B phase. In this, the one end is connected together. R phase, B phase, Y phase, one end is connected together. That is called a common point, either otherwise star point or neutral point, right? The other ends are taken out. These are the other ends are available. R phase, Y phase and B phase, right? Now we'll refer the line voltage and phase voltage. So here this side is called a line voltage or line current. Here inside the phase is called a phase voltage or phase current, right? VRY is the line voltage between R phase and Y phase. VYB is the line voltage between Y and the phase Y and phase B. VBR is the line voltage between this R phase and B phase, right? So VRY, VYB, VBR are the line voltage between the phases. Then IR line, the current flowing from the R phase is called IR line. This is called a line current. Similarly, current flowing through the RY is IY line. Current flowing through the B phase is IB line, right? So these three are line voltage, these three are line current. This line current is going to the phase. So the phase current also equal. Line current and phase current are equal. IR phase, current flowing through the R phase is IR phase. This IR line is equal to IR phase. Both the currents are equal. Line current is equal to phase current. Similarly, this IY line is equal to IY phase. Then IB line is equal to IB phase. Both the line current and phase currents are equal. Then what about the voltage? This is the line voltage, VRY. See, R phase is connected here and Y phase is connected here, right? So this VRY is the vector difference of R phase and Y phase, VR phase and VY phase, right? Because in between R and Y, two phases are available, R phase as well as Y phase, right? So VRY is the vector difference of VR phase voltage and VY phase voltage, because the current directions are opposite. So one voltage is positive, another voltage is negative. So that we are referring the phase difference of. Similarly, this VYB is connected between Y phase and B phase. So VYB is the vector difference of VY phase and VB phase. Similarly, VBR connected between B and R, right? Connected between B and R phase. So that is the vector difference of B phase and R phase, right? So in the star connection, it is important that line current is equal to phase current. Line voltage is vector sum of vector difference of phase voltage. That is the important relation we come to know. Line current is equal to phase current. Line voltage is vector difference of phase voltage. So based on that, we can go for the further relation between current and voltage. So that first we will refer the line voltage, VRY, VBR, VBY. The voltage between R and Y phase, voltage between B and R phase, voltage between B and Y phase. Both are equal because it is the balanced system. That is equal to VL. Commonly we will have line voltage, right? So voltage across the phases, commonly we will take it as VL. Then phase current, phase voltage, VR phase is equal to VY phase equal to VB phase, right? The phase voltage of R, the phase voltage of the R, phase voltage of Y, phase voltage of B, all are equal. Generally it is taken as V phase, right? Similarly, line current, IR line, IY line equal to IB line. All the line currents are equal. In general, it is termed as I line. Then phase current, IR, phase current of IR, phase current of IY, phase current of IB, all are equal. That is equal to I phase, right? So because of balanced system, the line currents across all the phases are equal, taken as VL. Phase voltage of all the phases are equal, taken as V phase. Line current of all the phases are equal, so it is taken as I line. Phase current of all the phases are equal, it is I phase. With this assumption, we will go to the relation between line and phase current. We already discussed the currents are equal. line current equal to phase current. The line current of R phase equal to phase current of R phase. Both are equal. Similarly, Y phase line current equal to phase current. B phase line current equal to phase current. So generally we can take IL equal to I phase. Line current equal to phase current. Right? So in the star connection, line current is equal to the phase current. Now we'll see the voltage, line and phase voltage. So while referring the voltage VRY, the voltage across R phase and Y phase equal to VR phase minus VY phase. Difference, vector difference of R phase and Y phase is VRY, line voltage. Similarly, VYB, line voltage equal to VY phase minus VB phase, because currents are opposite, so that we got negative sign. So the vector difference between VY phase and VB phase is VYB. Similarly, VBR, the line voltage of between the phase B and R equal to VB phase minus VR phase. So the vector difference of B phase and R phase is VBR, right? So that generally we can take it as line voltage is vector difference of two phase voltages, right? So current is equal, line current equal to phase current, but line voltage is vector difference of two phase voltages, right? With this relation we can go for the phasor diagram. So we'll go to the phasor diagram. So you already know that the line current is equal to phase current. Only the line voltage is the vector sum of the two phase voltages, right? So we are going to find the value of VRY, line voltage between R and Y, line voltage between B and R, line voltage between Y and B, right? We are going to find these three values. This is the vector difference. First we will refer the phase voltage, VR phase, opposite side minus VR phase, then VR, this is VY phase, right? Not R, VY. This is VY phase, and opposite side minus VY phase. Then VB phase, opposite side minus VB phase. All are displaced by 120 degree. VR and VY phase is displaced by 120 degree. VY and VB is displaced by 120 degree. VB and VR again displaced by 120 degree, right? So from phase voltage we are going to find the line voltage. First we are referring the phase voltage, VR minus VR, VY minus VY, VB minus VB. First we need to write the phase voltages, both positive and negative. Now we'll go to this VRY. VRY is the vector sum of VR and minus Vy, vector difference between these two, Vr and Vy, right? So vector sum of these two is nothing but Vry. We need to draw this line, right? By connecting this Vr and minus Vy, we got Vry. Similarly, Vbr is the vector difference of Vb and Vr minus Vr. So while by connecting these two lines, we got Vbr. Similarly, Vyb is the vector difference of Y phase and B phase, that is Vy and minus Vb, right? We need to draw this diagram, so that we got Vyb, right? So from phase voltage we are calculating the line voltage. These are all the phase voltages, Vr phase minus Vr phase, Vy phase minus Vy phase, Vb phase minus Vb phase. So all the phase voltage, both positive and negatives, are available. By connecting Vr phase and minus Vy phase, we got Vry, line voltage. By connecting Vb and minus Vr, we are getting Vbr, line voltage. By connecting Vy and minus Vb, we got Vyb, line voltage, right? So from phase voltage we are calculating line voltage. Now we'll refer the Vry. By using the parallelogram theorem, we can find the Vry. Vry is nothing but, it is the Vry is the vector difference of Vr phase and minus Vy phase. So that Vr square phase plus Vy square phase into 2 Vr phase Vy phase into cos theta. The theta is nothing but 60 degree. Here the 60 degree is nothing but a square plus b square plus 2ab cos theta. That is the formula available in the parallelogram. A square plus b square plus 2ab cos theta. Theta is here 60 degree. Now we can go for the further simplification. we already decided that the phase voltage, all the phase voltages are equal. So generally it is termed as V phase, right? Because of balance system. So that VR phase can be written as V phase square. Similarly, Vy phase can be written as V phase square in plus 2 into V phase into V phase. VR phase is equal to V phase. Vy phase is also V phase. Because of balance system, all the voltages are equal into cos theta, right? So we already discussed that phase voltages, all the phase voltages are equal because of balance system. Generally it is termed as V phase. So that all the voltages are replaced by V phase, right? So that V phase square plus V phase square plus 2 into V phase into V phase cos 60 is 1 by 2. So the 1 2 got cancelled. This become Vp square. V phase square. Already here V phase square available. Here one V phase square available. Here V phase into V phase is V phase square. 3 times available. So 3 V phase square. While taking square root, it is root 3 into V phase. V phase square it become V phase. So that line voltage equal to 3 times of phase voltage. That is the relation we got from this equation. Line current is equal to phase current. That already we got. From the parallelogram theorem, by using the phasor diagram, we got that line voltage equal to root 3 times of phase voltage. So similarly, we can find Vyb and Vb are also root 3 times of V phase, right? Here we calculated only Vry. While calculating Vyb and Vbr, that also we got only root 3 V phase, because everything we are replacing by V phase. So in star connection, line voltage equal to root 3 times of phase voltage. That is the relation we got. Now we'll go to the power calculation. So in the power calculation, P equal to V phase into I phase into cos pi. Similarly, 3 phases. This is for R phase, Y phase, B phase. Because of balance system, we have only phase voltage and phase current. So 3 times available, 3 VPH, IPH into cos pi. Phase voltage, line voltage into cos pi. This line voltage and phase voltages are equal. So that we can replace phase current by line current. But this phase voltage equal to VL by root 3, right? So that line voltage equal to root 3 times of phase voltage. So phase voltage equal to line voltage divided by root 3. This root 3 will come in the denominator. Phase voltage equal to line voltage divided by root 3. Phase voltage equal to line voltage divided by root 3. Right. Now phase voltage is replaced. Phase current also replaced. This 3 is written root 3 into root 3 for simplification purpose. Root 3 into root 3 is again 3 only. So VL by root 3 IL cos pi. This root 3 got cancelled. 1 root 3 got cancelled. So we have only root 3 VL IL cos pi. So the power in the 3-phase balanced star connection is root 3 VL IL cos pi. So in this video we discuss the star connection, balanced star connection, the diagram. What is the relation between current and voltage? The current is equal, line current equal to phase current. While analyzing the voltage using the phasor diagram and parallelogram equation, we got that line voltage equal to root 3 times of phase voltage. From that we calculated the power also. Power is root 3 VLIL cos pi. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we'll see the measurement of power in balanced 3-phase circuit by 2 wattmeter method. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic, measurement of power in a balanced 3-phase circuit by 2 wattmeter method. So this is the method for 3-phase power measurement, in which sum of reading of 2 wattmeter will give the total power of the system. So in order to measure the 3-phase power, we are using only 2 wattmeters. The reading of these 2 wattmeter will give the total power of the system. Now we'll see the circuit diagram. So this is the phase RYB. In phase R, 1 wattmeter is connected. In phase B, another wattmeter is connected. 2 wattmeters are connected. In phase Y, the wattmeter is not connected. So this is nothing but MLCV. the 4 terminals of the wattmeter. This is measurement line. So the common terminal, this is voltage, the MLCV, right? M is connected to R phase. L is connected to the line connected to the phase. C is the common terminal. V is the voltage that is connected to the next wattmeter, connected to another wattmeter. Similarly, here M is connected to B phase, L is connected to the phase of the winding, then V is short circuited. So reading of these two wattmeter will give the total power of the 3-phase system. Now we'll see how it will give the total power. So the load is considered as inductive load, and thus phasor diagram for inductive load is shown below. So we consider the inductive load. So there is a lagging and leading of current will occur. Now see this is the VR, and this is Vy and Vb. There are 3 voltages are available. This VR is the phase voltage, R phase voltage, Y phase voltage and B phase voltage, right? So Vy, this side we have minus Vy. So we have 3 phase voltages, VR, Vy, Vb. For Vy, we have negative of Vy minus Vy is available. We are going to measure Vby because wattmeter is connected in the B phase and R phase. So we are measuring Vby and Vry. Right? This is the voltage, connected voltage across R phase and Y phase. This is B phase and Y phase because wattmeter connected in R phase and B phase. Y phase is common. So this Vry is nothing but vector difference of Vr and minus Vy. There is a vector difference. So this vector difference of these two will give Vry. Similarly, Vby is the vector difference of Vb and minus Vy. The current direction is different, so that we are getting vector difference. This current of Ib and Iy is opposite side, so that we are getting minus Vy. So the vector difference of Vb and minus Vy will give Vby, right? So while calculating the power, what we need? Voltage, current and power factor. So for this, the wattmeter connected in the Ry, the R phase is, the voltage is Vry. The current is IR. What is the angle between VR and IR? It is 30 plus pi. The current is lagging by pi, angle pi. Right? Already the 30 degrees there. So 30 plus pi. So Vry IR into cos 30 plus pi. That is the power measured by the first wattmeter. Voltage Vry, current IR. The voltage, current and the angle between voltage and current is 30 plus pi. So that cos 30 plus pi. Another wattmeter connected in B phase. So the voltage is Vby. The current is Ib. This is current Ib. What is the angle between this? Current is leading here. So 30 minus pi. 30 degree already there. In that we need to subtract this angle. 30 minus pi. So Vby into Ib into cos 30 minus pi, right? So that is the reading of the second wattmeter. So from the phasor diagram it is very clear. So this is the phase voltage Vr, Vy, Vb. The negative of Vy is minus Vy. Vector sum of Vr and Vy is Vry. Vector sum of Vy and Vb is Vby. The reading of first wattmeter is this voltage connected in R phase. So Vry into IR cos 30 plus pi. The reading of second wattmeter is Vby connected in B phase. Vby Ib into cos 30 minus pi. Right? So we will see now how these two wattmeter reading will give the total power of the three phase system. The three voltages Vrn, Vyn and Vbn are displaced at an angle of 120 degree electrical as shown in the phase diagram, right? So these phase voltages are displaced by 120 diagram. The phase current lag behind the respective phase voltage by angle of pi. That also we referred. Ib and Iy we referred that, IR we referred that it is lagging by angle pi. The power measured by the wattmeter W1 and W2, right? So from the phasor diagram what we discussed, now we'll see the equation. Power measured by wattmeter W1 and W2. Reading of the wattmeter W1 is VRY into IR into cos pi 1. This cos pi 1 is nothing but cos 30 plus pi. We already discussed in the diagram, phasor diagram. So RY IR can be written as VL into IL because it is a balanced system. This is the line voltage and line current. VL IL cos 30 plus pi for the wattmeter reading 1. Wattmeter reading W2 is connected in B phase. VBY IB cos pi 2. Cos pi 2 is cos 30 minus pi. We already discussed in the diagram. Pi is available inside, so that 30 minus pi. So that VL IL cos 30 minus pi. Right? So we got the W1 reading and W2 reading. So the total power equal to P equal to W1 plus W2. Now we'll add these two and we'll verify whether it will give the total power of the three-phase system. So VLIL cos 30 plus pi plus VLIL cos 30 minus pi. Right. So VLIL is taken common. So cos 30 plus pi plus cos 30 minus pi. Cos A plus B is nothing but cos A cos B minus sin A sin B. So that cos 30 plus pi is cos 30 cos pi minus sin 30 sin pi. Similarly, cos A minus B is cos A cos B plus sin A sin B. So that cos 30 minus pi is cos 30 cos pi plus sin 30 sin pi. Here plus minus mean here plus. Here plus mean here minus. So this sin term got cancelled. 2 times of cos 30 cos pi. So VLIL 2 into cos 30 is root 3 by 2 into cos pi. So 2 got cancelled. So that what we got root 3 VLIL cos pi. So this is nothing but the total power of the three-phase system. So the 2 wattmeter reading while adding, we got that it will give the total power of the three-phase system. Thus the sum of the readings of 2 wattmeter is equal to the power absorbed in the three-phase balanced system. Right? 2 wattmeter reading while adding, we got the total power of the three-phase system. Now we'll see the power factor. We will analyze the power factor. So determination of the power factor from wattmeter reading. So as we know that W1 plus W2 equal to root 3 VLIL cos pi. Now we'll find W1 minus W2. In order to find the power factor, we need W1 minus W2. So VLIL cos 30 plus pi minus VLIL cos 30 minus pi. Right. So VLIL is taken common. Cos 30 plus pi minus cos 30 minus pi. So cos 30 plus pi is cos 30 cos pi minus sin 30 sin pi. This minus of already your minus available outside. Cos 30 minus pi is, as we discussed earlier, cos 30 cos pi sin 30 sin pi. Here negative means here positive. Here positive means negative. Now multiply this negative inside. So cos 30 cos pi minus sin 30 sin pi minus cos 30 cos pi, this become plus sin 30 sin pi. Right? So this cos term got cancelled. This cos term and cos term got cancelled. This is negative minus. So that what we got, it is nothing but VLIL 2 times sin 30 sin pi. Right? Negative sign is not a problem. This is also negative and this is also negative. Right? So that sin 30 is 1 by 2. So 2 got cancelled. This is sin pi. So VLIL sin pi. W1 minus W2 is VLIL sin pi. Now we'll see we'll go further how to measure the power factor. Root 3 W1 minus W2 divided by W1 plus W2. So this is the power factor. We find the power factor of this reading. So root 3 into W1 minus W2 is VLIL sin pi. W1 plus W2 is root 3 VLIL cos pi. So all terms got cancelled. Sin pi by cos pi is tan pi. Right? We are going in a reverse order. Tan pi. So we find the value for this expression. We got tan pi. So tan pi equal to root 3 W1 minus W2 divided by W1 plus W2. So that tan pi equal to tan inverse. This tan will go to tan inverse. Tan inverse root 3 W1 minus W2 divided by W1 plus W2. So we know that power factor is cos pi. That is equal to cos of pi value. Pi value is this one. Tan inverse root 3 W1 minus W2 divided by W1 plus W2. Right. So this is the power factor. From the wattmeter to wattmeter we can measure the power factor also. Now we'll analyze the wattmeter reading, the effect of power factor. I will see the effect of power factor on wattmeter reading. It is clear that lagging power factor cos pi 1 wattmeter readings are W1 equal to VLIL cos 30 plus pi, W2 equal to VLIL cos 30 minus pi. Right? We have W1 and W2. Thus, readings W1 and W2 will vary depends upon the power factor angle pi. So, base all are common. Only this pi will vary. If the pi varies, W1 and W2 value will vary. Pi increases, here added, here subtracted. So, the pi will decide the power factor. Now, we will analyze this reading with respect to the pi value. So, there a tabular column is available. 3 different cases are there. This is a power factor, pi value, W1, W2 remark. Suppose cos pi equal to 1 means pi value is 0. For pi 0, cos pi is 1. This is power factor. Cos pi is the power factor. In that pi is 0 means cos pi 0, that is equal to 1. Value is 1. What is the meaning? Cos pi equal to 1 means that is root 3 by 2 VLIL. Here also root 3 by 2 VLIL because pi is 0. Pi 0 means both the equations are equal. Both are equal and positive. Right? The pi value 0 means W1 is VLIL cos pi into cos 30. Similarly, W2 also VLIL cos 30. Both are equal. Suppose pi is 60 degree. Then cos 60 is 1 by 2, that is 0.5. Now we need to substitute cos pi equal to 0.5. In that case it is 0. W1 value is 0. W2 is root 3 by 2 VLIL. So one is 0, another one is, second is the total power. Suppose cos pi is 90 degree. Then cos pi is 90 degree. Pi is 90 degree means cos pi is 0. So we will substitute, by substituting cos pi equal to 0 we got minus 1 by 2 VLIL. This is plus 1 by 2 VLIL. Both are equal and opposite. Right? So 0 degree, pi 0 degree means both are equal and positive. 90 degree means both are equal and opposite. 60 degree means one is 0, another one is the total power. Right? So in this tabular column, this pi value is substituted here. By substituting the pi value, we are calculating W1 and W2. First case, pi value is 0. 0 means VLIL cos 30. VLIL cos, both are equal. So we have equal and positive degree. Second case, pi is 60. Means this is become cos 90. Cos 90 is 0. This value is 0. Here 30 minus 6 is minus 30. So that we got again root 3 by 2 VLIL. Suppose pi value is 90 degree. Means 30 plus 90, 120 degree. So we got negative value. 30 minus 90 is minus 60. We got positive value. These two values are equal and opposite. Right? So in this video we discuss how to measure the total power of the 3-phase system using 2 wattmeter method. We analyze the reading. While adding the two readings, wattmeter W1 and W2, we come to know that it will give the total power. From that we calculated power factor and also will analyze the effect of power factor on the wattmeter reading. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the 3-wire star connected unbalanced load. Details of star connected unbalanced load. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. 3-phase star connected with the unbalanced load. The balanced load video is available separately. This is the unbalanced load. So let us assume a phase sequence of RYB, red, yellow, blue, RYB. Then the reference phase voltage will be VRY. The voltage between R phase and Y phase is taken as a reference voltage, reference phasor. The 3 direction of current is shown in the diagram. The 3-wire star connected unbalanced load with conventional polarity of voltage and directions are given below. Now we'll refer the diagram so that we'll see the direction of current as well as the voltage. So this is the star connected. Star connected means three ends of RYB is connected to common point called a neutral point or star point. Then other ends are available at the output side, RYB. Right? Three ends are available at the output side. The one end of all three faces are connected together to form the neutral point or star point. Right? Now we'll see this RYB three phases. This is the current, line current. The line current between the two lines R and Y, VRY. VYB is the line voltage, this is the voltage, VRY. The line voltage between R phase and Y phase. Then VYB is the line voltage between Y phase and B phase. Similarly, VBR is the line voltage between R phase and B phase. Then this is the line current flowing from the R phase, IR. Current flowing from the Y phase, IY. Current flowing from the B phase, IB. So inside this is the phase voltage and phase current. This side line voltage and line current. Thereafter, once you enter into the load and the load end, this is the line end, this is the load end. Right. So VR is the phase voltage across the R phase. Vy is the phase voltage across the Y phase. Vb is the phase voltage across the B phase. Similarly, this IY is the current flowing through the Y phase. IR is the current flowing through the R phase. IB is the current flowing through the B phase. Here the important thing is this line current and phase current both are equal in star connected. The current flowing from the R phase, line current IR is equal to line current, equal to phase current. But the voltage is different. See this between R and Y we have VRY, but at this phase and we have two phases are available, R phase and Y phase. So vector difference of R phase and Y phase is the VRY. Right? VRY is the vector difference between R phase and Y phase. Similarly, the VYB is the vector difference between Y phase and B phase. Similarly, VBR is the vector difference between B phase and R phase. Right? So in the star connected, line current and phase current are equal, but the line voltage is the vector sum of two phase voltages. Right? So this is the conventional direction of current and voltage in a star connected system. Now we'll go for the further analysis. So the line voltage, we'll see the voltage and current. The line voltage of the supply or source for RYB sequence are VRY equal to VL, line voltage with 0 degree. This is taken as a reference vector, or RYB is a reference phasor. VYB is VL with minus 120 degree. We know that there is a 120 degree phase displacement between each and every phase. Each and every phase is displaced by 120 degree. So VRY is 0 degree means VYB automatically VL with minus 120 degree. VBR is the VL with minus 240 degree. There is a phase difference between these two is 120 degree. Between these two is 240 minus 0 means plus 120 degree. So normally it is 120 degree phase difference between each and every phase. VL is nothing but magnitude of the line voltage. Right? Magnitude of line voltage. Now we'll go further. In unbalanced star connected load, it will be easier to solve the line currents by assuming two sources across the line whose values are equal to the corresponding line voltages. Right? The line current we are assuming with the corresponding to line voltages. So this is the first assumption. Then consider the circuit shown below in which the voltage source value VRY is connected across R and Y. Right? VRY is the voltage across R and Y, and voltage source of the value VYB is connected across Y and B. Right? So we consider two things: VRY connected across RY, VYB connected across Y and B. Now we'll see the diagrams for the further analysis. So here the RYB is available. VRY is the voltage, line voltage across R and Y. VYB is the line voltage across Y and B. Right. So this is the line current IR, IY, IB. Then impedance ZR, ZB and ZY. For analysis we are going to form the KVL, Kirchhoff's voltage law, loop method. So we consider this is the first loop. Starting from R, ZR, ZY and Y is considered as the first loop. Current flowing through the first loop is I1. Starting from Y, ZY, ZB, then B is the second loop. With the current flowing in the second loop is I2. Right? So this is the first loop with current I1. This is the second loop with current I2. Now we are going to find the value of I1 and I2 using matrix method. Kirchhoff's voltage law with matrix method. Matrix method is V equal to I into R. We need to form the voltage matrix, current matrix and impedance matrix for loop 1 and loop 2. Right. The current is I1 and I2. The two current in the two loops are I1 and I2. The voltage matrix is VRY and VYB. Right. What is the impedance matrix? Impedance matrix is for the first loop, the impedance will be ZR plus ZY. Right. For the second loop, it is ZY plus ZB. These two are connected in the second loop. These two are connected in the first loop. What is the common between first and second loops is ZY. ZY is available in loop 1 as well as loop 2. This is ZY is common between loop 1 and loop 2. Right. So R11, Z11 is nothing but ZR plus ZY. Z22 is nothing but ZY plus ZB. Or Z11 means total impedance in the loop 1. Z22 is the total impedance in loop 2. Z12 or 21 is the commonly available between loop 1 and loop 2, that is ZY. So using that we can frame the matrix. Then we will analyze the current. See the current, this IR is nothing but I1. The current IR is nothing but, this is the current I1 is flowing in a loop. So IR equal to I1. Similarly IB is nothing but I2, but it's flowing in opposite direction. So IB is the minus I2. IR is I1. Both are equal. See the direction, both are equal. This IB is nothing but the current I2 is the IR, IB, but flowing in opposite direction. So IB equal to minus I2. What about this IY current? IY is I1 also flowing here. Then I2 also flowing. Right? Both are flowing in a opposite direction. I1 is flowing from this side to that side. I2 is flowing from that side to this side. Both are in opposite. So I2 minus I1 will give the IY. Right? The current IY is nothing but the difference between I2 and I1. Right? IR is I1. IB is I2 but negative. IY is difference between I2 and I1. Because in IY both I1 also flowing, I2 also flowing. So the difference between these two. So based on that we can go for the further analysis. What we discussed, we will frame the equation. So the circuits shown above have two meshes. We already discussed. Hence we assume two mesh currents are I1 and I2 as shown in the diagram. The mesh basic matrix equation is. So this is the equation we need to find. V equal to I into Z. V equal to I into R or V equal to I into Z. The V is VRY, VYB. The voltage in the first loop, voltage in the second loop. This is similarly current I1 and I2. Current in the first loop, current in the second loop. This is Z11. We already discussed. Z11 means impedance in the first loop. That is ZR plus ZY. Z22. This is impedance in the second loop. ZB plus ZY. This is nothing but Z12, this is Z21. That is the commonly available between loop 1 and loop 2. That is minus ZY. Other diagonal is positive. Other than diagonal, we need to treat it as a negative. So that minus ZY. So this is Z11 impedance in the first loop. Z22 impedance in the second loop. Z12 and Z21 both are same. The commonly available between loop 1 and loop 2 impedance. ZY. Right? Now framed the equation. Now we'll go for the how to calculate the current. By using this, we can calculate the current value. So that the delta is nothing but the matrix. The impedance matrix is the delta. ZR plus ZY minus ZY minus ZY, ZB plus ZY. So we can find the delta value. If we replace the first column with voltage, it will give delta 1. If we replace the second column with the voltage, that will give the delta 2. Right? So this is the impedance matrix is delta 1. In that the first column replaced with the voltage matrix will give the delta 1. Replacing the second column with the voltage matrix will give the delta 2. Now we got the value delta, delta 2 and delta 1. These values are not calculated, but we can calculate. So after calculating, we can easily find the I1 current and I2 current. I1 is delta 1 by delta. I2 is delta 2 divided by delta. So this is the formula. From this mesh current, the line current can be obtained as below. Right? After calculating I1 and I2, we can calculate the line current. Now we will see how to calculate the line current. As we already discussed, this IR is I1. Both the directions are equal. But IB equal to I2 but negative, minus I2. Then IY, both I2 and I1 is flowing. So that I2 minus I1. This thing already we discussed in the diagram itself. So IR is I1, IB is minus I2, IY is I2 minus I1. So this IY is both the currents are flowing. So the difference between these two. So now we got the line current. Right. In star connected load, the phase currents are the same as that of line current. We already discussed. Only the voltage is phasor difference, but the current, line current and phase current are equal. Therefore, the phase and line currents in the polar form can be written as. So based on that, we can write the line current in the polar form. IR equal to IR with angle of gamma R. IY equal to IY with an angle of gamma Y. IB is the IB with an angle of gamma B. Right. What is that? IR, IY, IB are the magnitude of line and phase currents. Gamma R, gamma Y, gamma B is the phase angle of the line and phase current with respect to the reference phases. Right. This is the angle corresponding line and phasor angle. Right. So we can go for the further analysis. Now the phase voltages are given by the product of phase current and phase impedance by using the Ohm's law applied to the AC circuit. So that VR equal to IR into ZR. That is VR with an angle of del R. Vy equal to Iy into Zy. Iy is we calculated, Zy already available in the diagram. That is equal to Vy with an angle of delta Y. Vb equal to Ib into Zb, that is equal to Vb with an angle of delta B. Right. So now we calculated the phase voltage also. First we calculated the loop current. From that we calculated the line voltage, line current. By using line current and impedance, we calculated the phase voltages, where VR, Vy, Vb are the magnitude of phase voltage. Del R, del Y, del B are the phase angle of phase voltage with respect to the reference phase. Right. So now we calculated current. The phase voltage is calculated from the phase current. Now we'll go for the power calculation. So power consumed by three-phase load P equal to power consumed by R phase load plus power consumed by Y phase load plus power consumed by B phase load. Right. The three phase is equal to power consumed by R phase, Y phase and B phase. Therefore P equal to magnitude of VR into magnitude of IR into cos phi 1 plus magnitude of Vy, magnitude of Iy plus into cos phi 2. Plus magnitude of Vb, magnitude of Ib into cos phi 3. We will see what is this pi 1 and pi 2 and pi 3. So that is equal to Vr Ir cos pi 1, Vy Iy cos pi 2 plus Vb Ib cos pi 3. Right. Now we will see what is mean by this pi 1. Pi 1 is the phase difference between Vr and Ir. Pi 2 is the phase difference between Vy and Iy. Pi 3 is the phase difference between Vb and Ib. Right. So now we calculated the power. Now we'll go for the further formula. What are the further formulas available? So pi 1 equal to del R minus gamma R. So del R gamma R we already discussed. Pi 2 is del Y minus gamma Y. Pi 3 equal to del B minus gamma B. right? So from these two angles we can calculate pi 1, pi 2 and pi 3. So pi 1 equal to pi r, pi 2 equal to pi y, pi 3 equal to pi b. So by using that we can calculate. So in this video we discuss the star connected unbalanced load, right? First we analyze the conventional current and voltage direction. Then by using Kirchhoff's voltage law mesh method, we find the I1 and I2 loop current. From that we calculated the line current. By using line current and impedance, we calculated the phase voltage. From that we calculated the power. In that we analyze the angle also. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the details about 3-wire delta connected unbalanced load. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. So this is the 3-phase delta connected unbalanced load. Balanced load, the video is available separately. Detail is given in the description box. This is coming under unbalanced load. Let us assume a phase sequence of RYB, red, yellow, blue. Let us the reference phasor be VRY. The voltage across R phase and Y phase VRY is taken as a reference phasor vector. The 3-phase delta connected unbalanced load with conventional polarity of voltage and direction of current is shown below. First we will see the conventional polarity of voltage and current for a balanced unbalanced delta connected. Now we will refer the diagram. So this is the RY phase, RYB, 3 phases available. This is delta connected. One end of the load is connected to another end of the another load. So it is connected end to end. All 3 loads are connected end to end. From that the 3 wires are taken out. So this side is referred as a line voltage or line current. This is the phase voltage or phase current. Right. So VRY is the line voltage between R phase and Y phase. VYB is the line voltage between Y phase and B phase. VBR is the line voltage between B phase and R phase. IR is the line current from the R phase. IY is the line current from Y phase. IB is the line current from B phase. Right. Thereafter this IY will go to R phase. It is splitted into 2. IRY and IBR. Right. The current is splitted. This is phase current. IRY is the phase current between R phase and Y phase. IBR is the phase current between IB and IR. Similarly, this IY is splitted into 2. IYB and IRY. Similarly, IB is splitted into IYB and IBR. Right. So the current is splitted. So IR is the vector's difference of IRY and IBR. Similarly, this IY is the vector difference of IYB and IBR. IYB and IRY. This IB is the vector difference of IBR and IYB. So the current is splitted. But see the voltage here. VRY is the voltage between R and Y. Same voltages appear across here also. VRY. Right? This is the phase voltage. This is the line voltage. Both are equal. Because the same voltages appear across line as well as phase. So in the delta connected, the line voltage is equal to phase voltage. But the line current is the vector difference of phase currents. Right? Just opposite to that of star connected. In star connected, the currents are equal, voltages are vector difference. Here, voltage is equal, current is vector difference. Right. So then we have the impedance ZRY, ZBR, ZYB. Now we'll see what is that. ZRY is the ZRY with an angle of pi RY. That is the angle between R and Y. ZYB is the ZYB with an angle of pi YB. ZBR is the ZBR with an angle of pi BR. Now we'll go to the current and voltage. Further analysis of the current and voltage of this unbalanced delta connected load. So the line voltage of the supply or source for RYB sequence are VRY equal to VL with an angle 0. We already discussed that VRY is taken as a reference. So it is equal to line voltage with an angle 0. VYB is the VL with an angle minus 120 degree. We know that there is a 120 degree phase displacement between each and every phase. Then VBR equal to VL into minus 240 degree, right? So each and every phase displaced by 120 degree, where VL is the magnitude of the line voltage. In delta connected load, the impedances are connected between two lines, right? We already know that the ZBR mean it is connected between B phase and R phase. ZYB means connected between Y and B. Based on that, we can go for further analysis. Hence, the voltage across the impedance connected between two lines will be same as that of line voltage between the two lines, right? The voltage across impedance is same as the line voltage. Therefore, the phase voltage will be same as that of line voltage of the source. This already we discussed. The current is the vector difference, but the voltage is same. Phase voltage equal to line voltage. Since the line voltages are balanced, the phase voltages of the load also balanced, even though the load impedance are unbalanced. So now we are analyzing the unbalanced load, but the line voltage is balanced, so that we assume that the phase voltage also will be balanced, even though the impedances are unbalanced. So we are assuming that condition. Based on that, we can go for further analysis. Therefore, the phase voltages are VRY equal to V with an angle 0, VYB equal to V with an angle minus 120, VBR equal to V with an angle minus 240 degree. What is that VL? V is nothing but VL magnitude of the phase voltage, right? We know that all are displaced by 120 degree. We assume that even the load is unbalanced, the line voltage equal to phase voltage. Based on that, we have 0 degree, minus 120 degree and 240 degree. The phase currents are given by the ratio of phase voltage and phase impedance. Now we calculated the phase voltage. From that, we can easily calculate the phase current. The phase current is nothing but is a ratio of V, I equal to V by R. V is nothing but phase voltage. R is phase impedance by using the Ohm's law in the AC circuit, right? The phase voltages are calculated. Now we are calculating the phase current. IRY equal to VRY divided by ZRY. That is equal to IRY with an angle gamma RY. IYB equal to VYB divided by ZYB. That is equal to IYB with an angle of gamma YB. IBR equal to VBR divided by ZBR. That is IBR with an angle of gamma BR. Right? Now we calculated the phase current. By using the phase voltage and impedance, we calculated the phase current. Now we will calculate the line current. We need to find the value of line current. So this IRY, IYB, IBR are the magnitude of phase current. Gamma RY, gamma YB, gamma BR as the phase angle of phase currents. Right? Now phase currents are calculated. From that, we can calculate the line current. By using KCL at node RYB, the line's current can be calculated as below, right? So we already know that the current is the line current is the vector difference of phase current. So that IR equal to IRY minus IBR, that we already discussed in the diagram itself. IYB equal to IYB minus IRY. IB equal to IBR minus IYB. Right? From the diagram, it is clearly given that current is splitted. So the line current equal to vector difference of two phase currents. Right? Now we calculated the line current also. First we calculated phase voltage, from that line voltage, from that we calculated the line current also. Now we'll go for the power calculation. Power calculation in the three-phase circuit. So power consumed by three-phase load equal to P equal to power consumed by R load, power consumed by Y load, power consumed by B load. That is P equal to magnitude of VRY into magnitude of IRY into cos pi 1 plus magnitude of VYB, magnitude of IYB into cos pi 2 plus magnitude of VBR, magnitude of IBR into cos pi 3. Right. What is that pi 1, pi 2, pi 3? Pi 1 is the phase difference between VRY and IRY. Pi 2 is the phase difference between VYB and IYB. Pi 3 is the phase difference between VBR and IBR, right? So that from this phase difference we can easily calculate pi 1, pi 2 and pi 3. So further some more details are available. Pi 1 equal to 0 minus gamma Ry. This gamma Ry already available in the previous expression. Similarly, pi 2 equal to minus 120 minus gamma YB. Pi 3 equal to minus 240 minus gamma YBR. These three angles are already available. These angles are decided is each phase is displaced by 120 degree. So from that pi 1 is nothing but pi Ry. Pi 2 is pi YB. Pi 3 is pi BR. Right? So in this video we discuss the unbalanced delta connection load. From the diagram first analyze the direction of phase voltage and phase current, line voltage and line current. Then we calculated the phase voltage, from that we calculated the line voltage, then we calculated the phase current, from that we calculated the line current. By using that finally we calculated the current, calculate the power calculation. In that we have pi 1, pi 2, pi 3, three angles are available. That expression also finally we evaluated. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.